Okay, so in this video we're going to talk about electrophilic aromatic substitution. But before we get into the electrophilic aromatic substitution, let's review a little bit about electrophilic addition in an alkane. If you remember from early chapters in 351, we have here our electrophile, we have a nucleophile. So basically for this reaction, we have our double bond acting on and grabbing our electrophile, getting as a product, we do have a formation of a carbocation and my electrophile being added. This is a slow step, rate determining step, because we have the formation of the carbocation. And now we have our nucleophile working on and doing the attack on a carbon, and we ended up, we call this hydrogens here. It's that particular molecule. Okay, remember this is a slow step, it's a rate determining step. We have the formation of the carbocation, and here's a fast step on where we have our nucleophile attacking our electrophile, and then we have the addition on electrophilic addition that we learned before. When we're talking about an electrophilic aromatic substitution, it basically imitates this particular mechanism here. So in an aromatic electrophilic aromatic substitution, we actually do have a benzene ring, okay, and we have hydrogens everywhere here, remember. So we need our electrophile, I'll call this a big Y, and on here we have a partial charge represented by the deltas. We have our double bond, we break the aromaticity on attacking and grabbing our electrophile. It's a slow step because we have the formation of a carbocation. We have that particular carbocation being formed, plus our Y minus. So let's just talk a little bit about that particular carbocation. On this carbocation is also called cyclohexadiene cation. It is a allylic carbocation. If we look at this particular double bond here, this carbocation is stabilized by the delocalization of this double bond. So the double bond starts moving. So we can claim the formation of resonance structures. So if we do have that, this double bond can move, and we can have the first resonance structure here. Okay. This double bond can delocalize, and we form that resonance structure. So we can claim that this is allylic position is stabilized, this carbocation is stabilized by the delocalization of the double bond. This particular carbocation is called cyclohexadiene cation. And on here, we have the formation of the first step. In the first step, we have we break the aromaticity, make this unstable carbocation. And we have two ways to go when you're predicting the final product. So we could have this on base, working as a base, this guy reaching electrons, grab the hydrogen, dump the double bond here, stabilizing our final product. restore the aromaticity. And now, or we could have this guy here. Let me change colors. Working as a base, working as a nucleophile, doing the attack here. And we have the addition of LY. Okay, so when we are predicting the final product for this particular reaction, electrophilic aromatic substitution, we do not claim the formation that this unrich electron molecule attacking the carbocation and working as a nucleophile. And the reason for that is because we have a driving force that try to restore the aromaticity. Remember, when we're talking about benzene rings, they're really stable because this ring here is aromatic. So if we do a nucleophilic attack and attack the carbocation, we ended up having a molecule that is not aromatic. So it's not stable at all. So instead, we claim that this guy rich in electron comes and working as a base, grab the hydrogen and stabilize the carbocation via restoring that double bond in there. And now this would be our final product. In this particular molecule, we have 3 resonance structures. We need to be able to draw them and show how the electron can flow. We say that the carbocation, the cyclohexadiene cation, is stabilized by the delocalization of the double bonds, as I showed here in this 3 resonance structures. And this is the mechanism reaction for the electrophilic aromatic substitution. So just as a review, the energy diagram for this particular, well, let me place this in here. So we have here the increase of energy, energy. So here we have our reactant, our benzene ring, that is our nucleophile, plus our electrophile. The first step on here is the formation of a carbocation. Let me lower this down a little bit. It's the formation of a carbocation, and we can show the intermediate by breaking this particular bond, making this bond and breaking this bond. So here we have the formation on partial charge associated with the formation of this carbocation and partial charge associated with my Y. On this part, we actually do have the completely plus charge. Okay, so this is my carbocation, cyclohexadiene cation. The next step we have here this guy working as our base. So on here we can show the restoring the aromaticity there. Here we have the hydrogen breaking and making bonds, our electrophile there, and that's our final product, a more stable product. Okay, so just looking again for this diagram, here we have our nucleophile, electrophile. So our aromatic molecule just works as our nucleophile, grab our electrophile, and on here we show that we have this breaking bond, breaking the aromaticity, higher activation energy required because it's really unstable molecule. Here we have our electrophile making the bond with my benzene ring, and then we have the formation of another nucleophile. This particular part, we have our carbocation, our cyclohexadiene cation being formed, where we have a full plus charge associated with this particular carbon. Remember, this carbon here, it's allylic position, so it is stabilized by the delocalization of these double bonds here, plus our nucleophile. On here, we have our nucleophile working as a base, actually, and grabbing the hydrogen, stabilizing again, forming again our aromaticity, restoring aromaticity, and making this acid, which is our final product, is more stable energetically compared to our initial product.